All right, so if we're taking a look, if you see redo or something like that on your combined gas well lab, you'll need to obviously go and redo that, because some of you guys, can't you just grade it like this? Well, the problem is that a lot of it would be wrong because you made mistakes right at the beginning. So if we take a look, combined, this is not the lab you just did. This is the one before. I went through and graded them. Some of you guys use T1 and T2, keeping it in Celsius. You've got to convert this whenever you're using this formula. Whenever you're using this formula down here, you've got to convert that to Kelvin. It says it right here. Don't forget to convert the temperature to the Kelvin scale. Right? Some of you guys did not do that. So you need to go back and do that. Make sure you get that done. The other thing is pressure 2 up here. Some of you guys have like 20 something. That's telling me that you went down here and you looked at whatever it is down here, but then you put that in for the pressure 2. You need to go down here and look right under this and see where it says subtract the value from P1. That result is your P2. It's telling you exactly what to do on this sheet. So you have P1 up here. You need to subtract that 20 whatever it is, and that will give you your new P2. So if you made one of those two mistakes, you would need to redo this entire thing because you would be starting with math down here that is completely incorrect. The other mistake that some people made is the volume of water entering the flask. This should be a lower number. So some of you guys have this, and you put that in as the V2. That is not the V2. You have this amount that entered the flask. You need to subtract that amount from V1. V1 is a completely empty flask. You subtract the amount of water that entered the flask, and that gives you the V2. So if you made a mistake on one of these variables, that messes up everything down here. If you made a mistake on one or more of the variables, like more than one of the variables, then yes, you are in some trouble here, and you won't get this right, and then you won't get this right. So I'm giving you the opportunity to complete that so that you can get those problems correct. Any questions about that or the laboratory that you guys did over the weekend or yesterday? Yeah, if you go back and watch this video, I mean, you can see I basically, again, gave you a lot of what you need to do there. So if you go back and watch the old Zoom, whenever the day of the laboratory, I give you a lot of what you're working with there, So hopefully you can get that done and get that turned in if you've not turned it in yet. I believe it's due midnight tonight. Okay. All right. Cool. Let's take a quick look at page 12, PV equals nRT. This is page 12 of our notes. It says density is defined as mass divided by volume. For a gas, density is usually labeled gram per liter. If you have 7.50 grams of Ne in a container at 25 degrees Celsius and 1 atmosphere, calculate the moles of Ne. And it says, do you really need the ideal gas law for this? Well, if you have grams of something, you can use grams per mole, or what's known as the molar mass, and get moles. So we have 7.50 grams of neon. Every 20.17 grams is 1 mole of neon. (7.50) divided by 20.17.
It's about 0.3718.
So that's 0.372 moles of neon. Then it says calculate the volume of the container. So we know that PV equals nRT. We have the temperature is 25, 273 plus 25.
It's 298.
So we have 298 Kelvin. We know it's 1 atmosphere. We know the moles. So we have P, N, and T, and R is the constant. So we're going to try to find volume. So we'll divide both sides by P. So we get 0.3. So I'm not going to be able to fit all that on there. So let's go ahead and remake this. .372 moles. 0.0821 atmosphere liters per Kelvin mole. I'm using this one because my atmosphere pressure P is 1. It's atmospheres. So that's going to go on the bottom. And my Kelvins are 298. 273 plus 25. So we get 0.372 times 0.0821 times 298 divided by 1. If we take a look here, atmospheres will cancel out, kelvins will cancel out, moles will cancel out. 0.372 times 0.0821 times 298 divided by 1.
The answer is about 9.1012.
So we get 9.10 liters. Then it says calculate the density. Well, density is grams divided by volume, or mass divided by volume. So we take the mass, which is 7.50 grams, and we divide that by 9.10 liters. 7.50 grams divided by 9.10 liters.
It's about 1.0001.
We get 1.00 grams per, 7.5 divided by 9.1.
The answer is about 0.8241.
There we go. 0.824 grams per liter. That's the density of neon. The density of oxygen gas is 1.14 grams per liter. If 5 grams of oxygen exert 2 atmospheres of pressure, what is the temperature? So they gave us the density, which means if we have the mass, we can find the volume. So 5.00 grams, every 1.14 grams is 1 liter. That's what density means. 5 divided by 1.14.
It's about 4.3859.
4.39 liters. That's the volume. We have the pressure. We want the temperature. We also need moles. To do PV equals nRT, we're going to need moles. Well, if we have grams, we have moles. 5.00 grams of oxygen. What do we know about oxygen? Looking at the periodic table, what is the formula for oxygen? Anybody? Oxygen. I'll open up the chat in case you're shy. There's oxygen on the periodic table. So its symbol is O, but it's not. What should it be? What does this little dot right here mean? No one. You got an idea? Very good. From the class, it says the formula is O2 because oxygen is diatomic. Nice job. So if we take a look here, that means that instead of 16, it's going to be 32 grams per 1 mole. 5 divided by 32.
The answer is about 0.1562.
So there's our N. We have our V. We have our P. We want to get the temperature. We need to divide both sides by NR. Cancels out there. Now it's just to plug in and calculate. 2 atmospheres. Volume, we calculated from the density. Number of moles, we calculated from the mass. R constant, since we're in atmospheres, 0.0821 atmosphere liters per Kelvin mole. Nope, moles will cancel out. Atmosphere liters will cancel out, leaving us with kelvins. It wants the temperature in Celsius, so we're going to have to do a little bit more than this, but 2 times 4.39 divided by 0.156 divided by 0.0821.
The answer is about 685.5304.
685.5. 685.5 minus 273.
It's 412.5.
That's 412.5 or 413 degrees Celsius. All right, only 2 more things left for the unit. Let's bring ourselves back to a little concept from last semester known as stoichiometry. A sample of solid potassium chlorate decomposes. So that means that this is going to break down to produce solid potassium chloride +1 -1. So that formula checks out. And oxygen gas. Well, somebody has already told us that oxygen is diatomic if we did not remember it from last semester. So that is O2. Looking through this, I can see that over here I have 3 oxygens. Over here I only have 2 oxygens. I need to find the least common multiple of 2 and 3, which is 6. So put a 3 here to get 6, and a 2 here to get 6. That leaves me with 2 potassium. I only have 1 potassium here. So I need to put a 2 there. I have 2 chlorines. So I need to, that 2 there also gives me 2 chlorines. So here's a balanced equation. 675 milliliters of gas was collected at 22 degrees Celsius. So right there, I know that's 0.675 liters. By dividing that by 1,000, I just got the V. 22 plus 273.
It's 295.
295 Kelvin there. And 754 millimeters of mercury. So 675 milliliters of oxygen gas were collected. So if PV equals nRT, I can solve for the number of moles of oxygen gas. And if I know that every 3 moles of oxygen gas that are formed, 2 moles of potassium chlorate must have broken down, I can use stoichiometry to calculate that. So the first thing I'm going to use the ideal gas law to get number of moles of oxygen. Pressure is 754 millimeters of mercury. Volume is 0.675 liters. Remember, I got to change that to liters because my R constant, or the R constant for this one, since I'm in millimeters of mercury, will be 62.4. Notice again, that's in liters, right? So that's why I got to make sure that my volume is in liters. 62.4 millimeters of mercury liters over Kelvin moles. And my temperature, 22 degrees Celsius, or 295 kelvins. Kelvins will cancel out, liters will cancel out, millimeters of mercury will cancel out. we will be left with moles of O2. 754 times 0.675 divided by 62.4 divided by 295.
It's about 0.02764.
That's how many moles of O2 I've got. 0.0276 moles of O2. Every 3 moles of O2 requires 2 moles of KClO3. I don't want moles of KClO3. It says how many grams. Every 1 mole of KClO3, K, 39.10, Cl, 35.45, O, 16 times 3. 16 times 3 plus 35.45 plus 39.10.
That would be 122.55.
The molar mass of potassium chlorate is 122.55 grams. So that will give me grams of KClO3. 0.0276 times 2 divided by 3 times 122.55.
It's about 2.2549.
2.25 grams of potassium chlorate. Bada bing, bada boom. All right, then there are some miscellaneous problems. Those are extra. Let's do one of these, and then we'll talk about Graham's law, and then we'll let you guys work on the review. So, stoichiometry, steps to identifying and solving gas problems with stoichiometry. Write a balanced equation if necessary. That's key, that's needed. Identify the givens and the needs. Determine whether permanent needs to be used or does not. The one we just did, we needed to use PV equals nRT. Other ones we may be able to use if it's at standard temperature pressure. Remember the molar volume that you calculated for the laboratory you just did. Every 1 mole is 22.4 liters. This is what volume of O2 at STP can be prepared by the decomposition of 2 grams of mercury oxide. Mercury oxide decomposes into mercury and oxygen. Decomposition, remember, is a breakdown. So I have 2 oxygen there, so I need a 2 there and a 2 there. So they tell me I have 2 grams of mercury oxide. $200.59 plus 16. So it's going to be 216.59 is equal to 1 mole. Every 2 moles of mercury oxide is 1 mole of oxygen. That would give me moles of oxygen. I could sit there and put that into PV equals nRT using standard temperature pressure. But since we are at standard temperature pressure, every 1 mole of oxygen also takes up 22.4 liters of space. That goes back to how we actually figured out that 0.0821. We used STP, if you recall, last week. So there we go. 200 divided by 216.59 divided by 2 times 22.4.
The answer is about 10.3421.
I said 200 instead of 2. 2 divided by 216.59 divided by 2 times 22.4.
The answer is about 0.1034.
0.1034. Looks like they may have used a different molar mass or something like that, but we get 0.103. Maybe they used a different periodic table. Remember, every answer I do is based off my periodic table. Everything cancels out except for liters there. Except for liters. For tonight, I'd like for you to try problem 2 on page 14. The last thing we've got for today, before this and the review, is basically looking at what would you call it? Graham's law of diffusion. It's also known as Fick's law. Fick worked a little bit after Graham, did a little bit more redeveloping, more specific law. But diffusion, if you bake bacon or you cook or bake a cake or you cook, eventually you get all these gas particles floating throughout your house. And if you're baking cookies, you start to smell vaporized chocolate and vaporized butter. You smell those cookies, right? Well, we know that kinetic energy equals 1/2 times mass, 1/2 the mass times velocity squared. That was last semester. We talked about that with thermodynamics. Hopefully you remember that. I'll write that down real quick. 1/2 mass times velocity squared. Kinetic energy, remember, is the energy of motion. If you were in my class last time, we dropped the balls, the styrofoam balls and stuff. So if we take a look at that, is kinetic energy. That's how fast something is moving. The faster something is moving, the velocity is compared to its mass on this. So if we take a look, mass times velocity squared. That equals your energy of motion. So in the room, if all of the gases have an average kinetic energy, we measure kinetic energy with what we call temperature. The temperature of something is an average kinetic energy of the particles. So in this room right now, we might measure this as 21 degrees Celsius. If we took that to an absolute scale, 21 plus 273 would be 294 Kelvin, right? All the particles in this room that are not Anna, right? It is Ann. That are not me or Ann or the light or the TV or something that gives off energy, right? Everything in this room that's not something that has an outside energy source, like us with the food, should be at that same temperature. If there are oxygen molecules in here versus hydrogen molecules, if they have the same amount of kinetic energy, the oxygen molecule is 32 grams per mole versus the hydrogen molecule, which is 2.02 grams per mole. So if these are the masses of these, that's the mass of the hydrogen, that's the mass of the oxygen per mole. They all have the same kinetic energy because they're at the same temperature in the same room. To get that amount from the hydrogen, that means the hydrogen particles must be moving faster. They must be moving faster. I believe that they must be moving about 4 times faster because the difference here is a factor of 16. And since the velocity is squared, the hydrogens must be moving about 4 times faster than the oxygens to have the same amount of kinetic energy. So smaller mass particles just one S, must move faster at comparable temperatures. Now, we've got this spray right here. This is, it says fart prank on it. If we spray this, we know that that will diffuse through the room. And normally what I would do is I'd go to the back of the room and spray it, and then we would see how long it took for this to move through the room. But we're not going to do that to ourselves this time. There's only 2 of us, and that's not worth the benefits of seeing it. But just like if you were baking cookies or something like that, this fart spray particle will move through the room. it's quite a large particle, so it moves rather slowly. If we used another small particle up front, maybe that smelled like flowers, something like ether, then we could actually watch how the flower smell would take over the front of the room quite quickly, while only the people in the back of the room would have the fart prank smell. So you can actually see these things move throughout the room. And you know it, sometimes you wake up and you're like, oh, mom's cooking bacon, right? But if the particle is smaller, it is going to move faster. The fart prank particle is quite large. So it moves rather slowly. The other thing is it kind of sticks there, you know, then if you're around it and you're stuck in there, it's going to be there for a while. You know, obviously it'll eventually diffuse, but it may take some time. So I would like for you to try problem number 2 for tomorrow. And I also would like for you to download and work through this review today and tomorrow. Let me show you where that review is. So it says work through gas law review for test on Thursday. So if you would take a look, that problem in this review should not take you too long. It's all the way back what we were dealing with a few weeks ago. A lot of these nice things are, you know, in the notes. And then it does have some problems for you to do. Those problems will be similar to that combined gas law homework. And also it will include PV equals nRT. And then the things that we talked about today. Gases move at different speeds according to their molecular weight. Put the following gases in order of increasing speed, slowest to fastest. So you will need to look at the weights of all these, the molecular weights of all these, and then the lower the weight, the faster it's going to be. So hydrogen here would be the fastest. And then it looks like nitrogen, 28, would be second fastest, and then argon would be third fastest, and then chlorine at 70.9 would be the slowest. That's kind of good, you know, if you were out there and chlorine gas was coming towards you, you would want all the time you could get to get away from chlorine gas. If you've ever read All's Quiet on the Western Front, is that a required book anymore? It's about World War I. And basically the trench wars. Chlorine gas not only travels slow, but it's also very dense. So if you dug out a trench, that chlorine gas would get stuck in that trench. So basically you had two choices if you didn't have a gas mask: die from chlorine inhalation, which basically turns your lungs into a liquid, not very pleasant, or get out of your trench and then get mowed down by a machine gun fire. So yeah, it's pretty dismal. This is 1, 2, 3, 4 pages. We will go over the answers to this tomorrow. If you have any questions, and then test Thursday. That's all I've got for you today. Hopefully you got the laboratory done, but that's the week. That's the week in the lookout for the week. Have a great day. If you have questions, by all means, stick around. We'll try to answer those. Otherwise, get out of here, print that out, and get work. Would you like a copy of it printed? Yeah, all right. Have a good day. That's one of the benefits you get, right? Printed copies. Man, they all jumped. Nobody's got questions. I was thinking there were going to be more questions. Boom, 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 boom. Oh, I should stop the recording. They bounced.